Hi, and welcome to mini lecture 3 for week 12 of the Quantum Universe for Educators. This week we're going to go through an example of Bell's theorem and discuss how it allows us to distinguish between quantum mechanics and local hidden variable theories that are proposed to replace quantum mechanics as a more fundamental theory. So Bell's theorem was published in 1964, directly inspired by the EPR paradox that we covered in the previous lecture. And what it is a proposed experimental test in which, if you take quantum mechanics at face value, a non-local theory, in which the measurement of the property of one electron could instantaneously affect the properties of another electron billions of miles or even light years away, then in the experiment that Bell proposes, that non-local quantum mechanics gives a different prediction to the prediction of local hidden variables theories, which Einstein was arguing for in the EPR paper, in which the two electrons do not affect each other at all, but rather they carry extra information with them. They have extra properties that quantum mechanics doesn't describe. Now, the proposed experiment was actually carried out, most famously in 1982, and the result of this experiment is one of the most important results in the history of science. And it's so important, I'm going to state it up front before we even get into Bell's theorem. So, spoilers for the next slide. The experiment of 1982 showed that local hidden variables theories are not correct, that Einstein was wrong, and that nature really is non-local, as quantum mechanics predicts, at the fundamental level. Okay, so Bell's theorem we're going to illustrate using the thought experiment that was devised by David Mermin in his 1985 Physics Today article, Is the Moon There When Nobody Looks? So he came up with a thought experiment version of the experiment that Bell proposed. And it allows us to illustrate Bell's theorem in as easy a way as possible. And at the end, we'll explain how this connects with actual real physical systems. In Mermin's experiment, you have a source of particles at the center here, and every now and again it spits out two particles in opposite directions. And then you have two observers, A and B, often referred to as Alice and Bob, who have two detectors, and they detect these particles. Now, the way their detectors work is as follows. Both Alice and Bob's detectors have a switch that can be set to one of three settings. So this is depicted by these circular dials at the bottom here. So you can imagine turning the dial so that it points to either 1, 2, or 3. And both Alice and Bob are free to turn it to whichever of the three settings they want. In each of the three settings, whenever Alice and Bob's detector detects a particle, it'll flash either red or green. And it will always flash either red or green when it detects a particle. So when two particles are emitted by the source in opposite directions and are detected by Alice and Bob, we can write the outcome in the following way. A sequence of two numbers and two letters. The two numbers refer to the settings that Alice and Bob have set their detectors to. So in this example here, 1, 3 means Alice has set her detector to 1 and Bob to 3. And then the two letters refer to the two colors that Alice and Bob's detector light up with. So in this example, Alice's detector, which is set to setting 1, that lights up red, and Bob's detector, which is set to setting 3, lights up green. Now, we conduct the experiment by repeatedly sending out pairs of particles to be detected by Alice and Bob. And between each detection, Alice and Bob randomly reset their switches. Now, Alice and Bob do not communicate with each other. They have no way of knowing what they've set each other's switches to, so the settings are entirely random. They collect their results together, and at the end of the experiment, they compare the results and they can collect them together and display them as a sequence of 4 characters like this. So the results of, in this case, 45 separate pairs of particles sent out and detected by Alice and Bob result in 45 results like this. So the first one, in the first result, Alice had her detector set to 3 and Bob to 1, and they both flashed red. And the second one here, Alice set her detector to setting 1, Bob to setting 2, Alice's detector flashed green, Bob's red, and so on. Okay, now this is what they would notice in their results. They would notice firstly that whenever their switches are set to the same number, then their lights always flash the same color. So here we have Alice's detector set to 2, Bob's is set to 2, and they both flash green, and so on. So that's one thing they notice. However, if you just look at the colors and ignore what the detectors were set to, the colors themselves are still completely random. So it's completely random. So Alice detects red and green in a completely random sequence, and so does Bob. Okay, now if they count up out of all the possible results how many times their detectors both flashed the same color, then they would find that their detectors flash the same color exactly half of the time if you conduct the experiment long enough. So Alice is setting her switch to 1 or 2 or 3. If it's set to 1, then Bob can set it to 1, 2 or 3. Bob's detector could be set to 1, 2 or 3. If Alice's is set to 2, then Bob's detector can be set to 1, 2 or 3, and so on. And this here is just a picture showing the position of the arrows of the dials of Alice and Bob in these cases. So in this case, both Alice and Bob set their dials to 1. That means the arrows are both pointing up. They find the following probabilities of getting the same color with their switches set to each of these 9 possible settings. So you'll notice that if their dials are set to the same number, so 1, 1, 2, 2, or 3, 3, then as we saw before, the probability that they will observe the same color on their detectors is 1. Right? So they always observe the same color when their dials are set to the same settings. When they're not set to the same settings, they always see the same color exactly 1/4 of the time. Okay, so you can add up all these probabilities to find the overall probability of observing the same color on their detectors, and what you will find is that they detect the same color exactly half of the time. This is the outcome you expect from quantum mechanics. Okay, now in a hidden variables theory, the way a local hidden variables theory would try and explain this experiment is that the particles that are emitted carry with them a set of properties or a set of information, often referred to as instructions, and these instructions are just the hidden physical variables that we don't know about yet, because we haven't discovered the deeper theory underlying quantum mechanics. So if there is this deeper theory which contains these extra variables associated with these particles, then this might be how the experiment goes. Now, there are 3 possible positions you can set the switch to, 1, 2, and 3, and there are 2 different colors that the detector can flash. So to cover all possible outcomes, you need the particles to carry with them one of 8 possible sets of instructions. Red, 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 green, red, green, red, red, green, green, and so on. And these instructions tell the detector what color to flash when the particle is detected and the switch is set to a particular position. So for example, if a particle is carrying with it instruction set 0, this tells the detector if the switch is set to 1, flash red. If it's set to 2, flash red. If it's set to 3, flash red. If, on the other hand, the particle is carrying with it instruction set 4, then that says if the switch is set to 1, flash green. If it's set to 2, flash red. If it's set to 3, flash red. Now, when the particles are emitted, they are given one of these 8 instruction sets with a probability that is given by these 8 probabilities, P0 to P7. So, for example, if it was completely random which of these 8 instruction sets a particle ended up with, then these probabilities will all be the same. They will be 1/8. Our deeper theory could set these probabilities to any value we want, so long as they all add up to 1. Okay, so given this, we can actually calculate the probability that we will see both Alice and Bob's detector flash with the same color. All you have to do is count up for each instruction set how many of all the possible combinations of switches, how many give you the same color and how many don't. And then you add up all those probabilities. So for example, if the pair of particles are both emitted with instruction set 0, then both detectors will always flash red according to this instruction set. So you get the same color 100% of the time. If both particles are sent out with instruction set 1, then only 5 of the 9 possible combinations of switches give you the same color. The other 4 do not. So this possibility gives you the same color only 5/9 of the time, and so on. I should note, by the way, that in this hidden variables theory, in order to explain the results, both pairs of particles have to have the same instruction set, although the next pair of particles that are emitted may have a different instruction set, and so on. So you can add up these probabilities. Okay, so the instruction set 0 is assigned to the pair of particles with a probability of P0, and so the probability of the same color is 9/9 times P0 plus, then we move on to the next possibility. Instruction set 1 has a probability of P1, and if you have that instruction set, you get the same color 5/9 of the time. So you add all these up and you get the result that the probability that you have the same color is 5/9 of times this number alpha plus 1 times this number beta. Alpha is just P1 plus P2 plus P3 up to P6, and beta is just P0 plus P7. Alpha and beta themselves have to add up to 1 because probabilities have to add up to 100%. And so we can rearrange the formula using that information to finally get the probability that the particles have the same color is 1 minus 4/9 times this number alpha. Now alpha, again, is just the sum of the probabilities P1 to P6. These we are free to adjust. All right, our deeper theory presumably is going to predict what these probabilities are, but we don't know what that is yet. So they could be anything so long as they're between 0 and 1. So the smallest possible value alpha could be is 0, which corresponds to all of these probabilities being 0. In that case, the probability that you'll find the same color is 5/9. And if alpha is the smallest value it could be, then this overall probability is the largest it could be, right? Because if alpha is any bigger, then 1 minus 4/9 of alpha gives you a smaller result. So the smallest probability that you can get out of a hidden variables theory for finding the same color is 5/9. But in our experiment, we got a half, which is less than 5/9. No hidden variables theory can give us a probability as small as a half. All hidden variables theories give us a probability of finding the same color of 5/9 or greater. So if we actually conduct an experiment like this in real life, and we find that our probability of finding the same color, of course, in real life, color is going to mean some physical property of the particles. If we find the probability is less than 5/9, then we have disproven hidden variables theories. Okay, so there are several ways you could do this. The way that we would be familiar with is using electrons. Okay, you send out electrons in an entangled state so that if one is spin up, the other is spin down. If one is spin down, the other is spin up. And before they're measured, they are in a superposition of both of those states. In that case, the 3 switches that we are free to set the detector to correspond to 3 possible spin states. So you could imagine when you turn the dial in your detector, what you're actually doing is turning the magnets of a Stern-Gerlach apparatus to 3 different directions. So they could be in the XYZ directions, or they could just be in the Z direction, 60 degrees to the Z direction, or 120 degrees to the Z direction. It doesn't matter. And then the different colors, red and green, correspond to measuring either spin up or spin down along that direction. The most accurate test of this by Alain Aspect in 1982 actually used photons instead of electrons in different polarization states. And their result, as I mentioned before, is one of the most important results in all of science, because when they measured the probability of finding both photons in the same polarization state, they found that probability agreed with quantum mechanical predictions. They found results that agreed with non-local quantum mechanical predictions, but they violated Bell's inequalities, which means that they ruled out hidden variables theories. And notice here it says they're ruled out by 5 standard deviations. In other words, 5 standard deviations means that given the results of this experiment, the chance that local hidden variables theories are correct are 0.000000001%. In physics, just like in law, we have a concept of reasonable doubt and what constitutes beyond reasonable doubt. In physics, it's very precise. If you're beyond 5 standard deviations, then you are beyond reasonable doubt. So experiment tells us that nature is non-local at the fundamental level, that making measurements of a system in one place can potentially affect the outcome of a measurement at the other side of the universe instantaneously. Einstein was wrong. Quantum mechanics really is that weird. You can't save it by assuming there is some underlying theory we haven't discovered yet. There is no underlying local hidden variables theory.